Hi everybody, we are back and today we're going to talk about biconditional introduction and biconditional elimination. So if you don't remember, the biconditional was the triple bar. Just like that. And the idea that we associated with it was if and only if. Now, that by itself might not mean much to you. You're thinking, if and only if, what the heck is that? Well, what it is it's two if-then statements put together. If you remember when we had the if-then statement, if A, then B, it was kind of like there was an arrow leading us from A to B, the direction of the conditional. Now this one is the biconditional. It's like two of these. So here we have if A, then B. It's kind of like also having if B, then A. So here we have an arrow going this way and an arrow going that way. All right, so the simplest way I can think of to describe the biconditional is saying it's a fancy equal sign. So whatever's on this side is equal to what's on that side. So say I have A triple bar M. That tells me if A is true, then M has to be true. It also tells me if M is true, then A has to be true. So whichever side you have first, that'll tell you that the other side's true too. So in this case, something that might go with that expression would be, in Spanish, the word manzana means apple. So the words apple and manzana are kind of equal to each other. They both mean the same thing. So if something is an apple, then it is a manzana. If something is a manzana, then it is an apple. And then overall, something is an apple if and only if it is a manzana. So you can see in that way it's kind of like two conditional statements combined. So the rule is actually going to look a lot like our conditional rules. All right, so let us take a look at the biconditional introduction first. All right, here is our biconditional introduction rule. And you can see that at the end of it, we have derived a biconditional. So this is one of the rules that requires subderivations, which is where we draw our own separate scope lines inside to test our own assumptions. And what's going on here is since the biconditional means that P is equal to Q, in order to prove that, we have to experiment. We have to start with P and see if we can get to Q, and then we have to go backwards so we can start with Q and get ourselves back to P. So that's what's going on here in this rule. In our first subderivation, we make the assumption P, which is the first part, and then through whatever method we can, we derive Q. And then we go backwards. We start ourselves another subderivation, start with Q, which is the second part, and get ourselves back to P, which was our first part. So it's proving that we can go both ways with this one. And the way we cite that is here we do lines 1 through 2, however long the first subderivation took us. And then we cite the second part of the subderivation, the second separate scope line that we had to draw. Here it's lines 3 through 4. And then finally, we write biconditional, so we do our triple bar, and then an I for introduction. So when we're proving a biconditional is true, we have down here the biconditional that we want to prove. We'll draw ourselves two subderivations, separate scope lines. In the first one, we assume the first part and get to the second part. Then we assume the second part, get ourselves back to the first part. And so there would be more things happening in there depending on how much information we had in the problem. So that is biconditional introduction. Now let's take a look at biconditional elimination. All right, here is our biconditional elimination rule. And what it tells us is that if we have a biconditional on one line, and then on another line we have the first piece of it, then we know that the second piece of it is true. So this one says P is true if and only if Q is true. And then it tells us that P is true, so then we know that Q is true. And what we do to cite that is we cite the line where we saw the biconditional, the line with the triple bar, then we saw the line where we saw the first part of it. And then we write triple bar elimination. That's how we got rid of the triple bar and proved that Q was true. Now the handy thing about a biconditional is that unlike a conditional, this one goes both ways. So, just like this, what if we didn't know that P was true? What if we knew that Q was true? We knew that the second part was true. With that information, since we know if this part is true, then that has to be true, and if that part is true, then this has to be true, if they give us the second part of a biconditional, we know that the first part is true. So that is the way it works. If you have the first part, you know that the second part's true. If you give the second part, then you know that the first part's true. So this is a really handy rule, and it all comes from the fact that a biconditional is like an equals sign. So if you've had math, you know that when one thing equals another thing, you can substitute that in for the first part, for the first expression. So it's like P is equal to Q. You know you have Q, so now you know you have P. All right, so that is the biconditional introduction and biconditional elimination rules.